Hello everyone. In this video we are going to perform analytical forward and inverse kinematics. For the Stanford Arm, the RRP configuration that you can see, revolute, prismatic with a spherical wrist and then the end effector. And we're going to use DH convention. So there are some distances that are important here. There is distance of D1, D2, D3, and D6. So let's go ahead and get started with the forward kinematics using DH method. So first we set up the z-axis. Definitely z number 0 is going to be upward. So let's go ahead and do z number 0. So it is going to look like this. So that's z number 0. Then we go to z number 1, and z number 1 is going to be along this axis here. So let's do that. This is going to be z number 1, right? Something like this, or I can bring it a little bit off here. Then we have z number 2, which is aligning the motion of the prismatic joint. So it is going to be something like this. Then we have z number 3, this rotation here, right? And then like this. Then we have z number 4, which is the upward rotation. Then we have z number 5, which is similar to z number 3. And finally, we have z number 6 if you use the NSA approach, and for NSA method, or for the A or approach, we use z as typically suggested. Then this is going to be the z direction for z6. Okay, so these are the z's. Let me write them down for you here. Right, so z0, z1, z2, z3, z4, z5, and z6. Okay, so now we go and set up the origin. For frame 0, it's arbitrary. You can choose any direction that you want for x and y and any location for origin. If I use the bottom of the robot, that is going to be a convenient location. Now for x and y, you can choose any direction that you want, but before that, in order to minimize the amount of non-zero parameters in the table, or minimize the amount of transformations, I first look at x1, then I'll try to match x0 with x1 as much as possible. So for x1, if I look, z0 and z1, you see they intersect at this point. So that is going to be origin of frame 1, and then x1 has to be perpendicular to z0, intersecting it, and naturally perpendicular to z1. So the only solution for that is to be basically in this direction along this line, right, which is perpendicular to the member and perpendicular to the upward direction. So I can choose any direction either along this line, either to the top left or bottom right, right? I can choose that. So here I choose this backward direction here, and I say, well, let me choose that to be my x number 1, okay? If you choose that to be your x number 1, then your x0 can match x number 1. So the only amount of rotation you need here is just theta 1, not theta 1 plus some extra angle. Okay, so here I choose my, as I said, x number 0 to be the same as x number 1 when theta 1 has not rotated yet. Okay, so this is going to be my x0. If that is the case, then the only solution exists for y0 is going to be to parallel to Z1 basically, right? So it is going to look like this. Is going to be y number 0. And so now your frame number 0 is complete. Your frame number 1 is also complete because you have x1 and z1. So y1 has to be upward or downward. And here the only solution is downward. So here we go. I set up my y1 as well. So this guy is going to be my y1. And then now I go to frame number from 1 to 2. Again, you see Z1 and Z2 already intersecting at this point, right? So that has to be also the origin of frame 2 for me, and X2 has to be perpendicular to Z1, naturally to Z2, intersecting Z1. So the only solution for it is to be up or down. Okay, and you can choose any that you want here. So let's go with the up direction here. So we choose this guy to be my up direction, and that is going to be my as I said, x number 2, right? And let me move this Z1 a little bit off here, so bring it here or somewhere that I can read it. Z number 1. Okay, so that is Z number 1 here. X2, Z2, and Y2 definitely has to be radially out like this. So these are the first 3 frames. Now for spherical wrist, we know that we typically choose the intersection point, the wrist point here, to be the origin of frames 3, 4, and 5. And I can explain that why that's the case. Before that, let me emphasize that here distances D1, D2, and D6 are fixed distances, but distance D number 3 is the joint variable. Okay, so D number 3, I put a star next to it. That's the joint variable, that's the prismatic joint value, so that's not a fixed distance. So now going back to these spherical wrist axes, Z2 and 3 are parallel, so the origin of 3 can be arbitrary anywhere along Z3. 3 and 4 intersect at the wrist point, so that's origin of 4. 4 and 5 intersect at the wrist point, so that's origin of 5. So you see already origin of 4 and 5 are at the wrist point, and that's why, because I can select my origin of 3 arbitrary, I choose that to also be at the wrist point. That way I have 3 origins at the same place, and that makes the set of D's and A's for all of those to be 0. So that minimizes the amount of non-zero parameters in my DH table. That makes my A matrices later simpler. So what I do here, I choose my origin of 3 to be at the same place as 4 and 5. And for that reason, here I can basically extend them like this. Okay, and then say, well, your Z5, which is this guy, is also your Z number 3. Okay, because the Z number 3 is starting from that wrist point. Now that is the case, I can go ahead and set up my X number 3. And your X number 3 has to be perpendicular to Z2. Right? And Z3, which are parallel and intersecting Z2. So in this case, it can be upward, downward like Z4, or it could be radially in, radially out like Y2. And here I choose the radial direction. Y, again, although if I choose the X3 to be similar to X2, that makes this theta that I need 0. And if I choose it right now to be radially outward like this, that makes my theta to be non-zero, but that makes some of my future thetas simpler. Why? Because I'll show you here. Let me select this to be x number 3, right? Z3 is that, and then y has to be definitely upward or downward. In this case, it has to be upward, so it is going to be similar to z number 4. So let me write it down for you here. This is also y number 3, this z4. That's also y number 3. Now, why did I select this direction? Although it makes the theta for 2 to 3 non-zero, because now if you look at x4 and 5, you'll see that your z3 and 4 are already perpendicular like that, and x4 has to be in the same direction as x3 is. So if I choose this to not only be x3 but to also be what? x4, now x3 and 4 are aligned. Okay, let me show y4 and then I go to x5. So y4 definitely with that z and that x, it has to be the same direction as z2 or z6, right? And here definitely the same line, the direction has to be backwards. So it is going to be like this. That direction is going to be y number 4. And now again, if you look, z4 and z5 are perpendicular like that, and that makes my x5 to be the same direction. I can choose it to be the same direction of x4. And that makes 2 of my future thetas to be 0. Plus, of course, the angle that I have, theta 4 or theta 5. But it reduces 2 of the offsets here. Instead of last time I chose x3 to be the same as x2 but different from these, right? So instead of 2 non-zero offsets, if I chose it the other way, I would get 1 non-zero offset, and of course this is better solution than that one. So this is how I select x5, x3, x4. z5 is that way. And with that the case, then your y has to be, in this case, the same as y3. So your y3 is going to be similar to here, and now you get to 6. For 6, y has to be up or down, because that's the direction of opening and closing or slip, and x is going to be perpendicular, of course, to z5 and 6, and it is going to be the normal direction here. It is up to us how to select x6. I personally prefer to be the same direction as x3, 4, and 5, especially 5. So I choose my x number 6 to be like this. If you look at the web, there is a separate solution that makes x6 to the right, but I don't see any reason we should do that. And that definitely makes your y number 6 to be the same as y number 5 upward, but in a separate location, of course, here. Okay, so this is my whole set of DH axes or axes. And now I'm ready to fill my table. Going from frame 0 to frame 1, the x's are aligned already. The only rotation I need is theta 1 about z0, and that is going to be written down here for me. So let me write it down here. This is definitely going to be theta number 1, and that is your joint variable. I need to move along the old z a distance of constant d1 to set the origins. I don't need any motion along x1. I will write it down as d1 and 0, and then you look at the z-axis. The z's are definitely not aligned. You need a twist. So z0 is upward here, and z1 is to the right. and then your x1 is like this. Now positive direction for x1 is going to be this way, but the rotation you need to go from z0 to z1 is opposite of that, as you can see. So that angle has to be what? Negative 90 degrees. So let's go ahead and add that here. Negative 90 degrees, correct? Takes you from z0 to z1. Now we go from frame 1 to 2. If you look at the x's, they are not aligned in the first place, right? x2 is upward, x1 is to the right. So without even theta 2 being applied, you first need an offset angle, and then you can apply your theta 2. So this is your x0, this is your x1. Your x2 is upward, and then you have your z number 1, which is this. So positive rotation for this z1, it is going to be this way, and that is opposite to the direction that you need to align x1 with x2, so that's negative 90 degrees, and then you have your angle theta 2, correct? Because if you remember, your angle theta 1 is going to be applied around z0. So let me draw that for you here. Right, that is your theta number 1. Then your theta number 2 is here. So definitely that will make this angle here for you theta 2, and then minus 90 degrees. Okay, so for that, here, let me write it down again for you. This is theta 2 star minus 90 degrees. Now, to align the origins, you need to move along old z, or z1, a distance constant of d2. Then the origins will automatically be aligned. No a is needed, so a is going to be 0. And then we look at the z's. So z1 and z2, again, they are not aligned. If you can see, that is your z1. Your z2 is going to be in this direction, and your new x2 is upward. So positive direction for x2 is going to be like this, and that is aligned with the direction that you need to go to align z1 with z2. So that is going to be positive 90 degrees. Now we go to 3. For 3, we first look at the x's, x2 versus x3. Again, you see they are clearly not aligned. So although this joint has no theta variable, but you need a non-zero theta rotation to align the x's, because that's your x2 and this is your x number 3. And your old z, which is z2, is like this. Positive direction for z2 is going to be this way, and that is opposite to the direction that you align what? x2 with x3. So you have a constant of negative 90 degrees here for theta. So let's write it down here. Do you need to go from origin of 2 to origin of 3? How much of d do you need? That distance is called d3, and that d3 is your actual joint variable. Okay, that's the prismatic joint. So it is d3, but it is the star d3 because it is variable. And that's all you need. There is no motion along new x's needed. So a 0. And what about the z's? Well, that's your z2. Your z3 here is clearly, if you look at it, that is parallel to z2 already. So no rotation about x3 needed to align them. So twist is 0. Then you go from 3 to 4 and 4 to 5. In both cases, since the origins of 3, 4, and 5 are on the top of each other, no D or no A is needed. Now, what about the X's and Z's? So first we align X3 with X number 4. And as you can see, they are already aligned. So the only thing that you really need is the rotation of theta 4 to happen, correct? It is going to be like this. That is your theta 4. The same thing happens for theta 6, correct? So your theta 6 is also going to be like this. And your theta number 5 is going to be about this axis. So again, since the x's are already aligned, all you need is really theta number 4. And that is the joint variable. What about the z's? Well, z3 and z4, they are not aligned. So we need to align that here. And here, if you look, your z3 is this way, and your z4 is upward, right? So that's your z number 3. This is your z number 4, and new x number 4 is like this. So rotation that you need is this much, 90 degrees, and that is opposite to the positive direction of rotation about x4. So definitely that rotation is going to be negative 90 degrees. Now you look at x4 and 5, again aligned. All you need is theta number 5 to, in general, align them. And if you look at z's now, your this is going from 4 to 5, so z4 is the same, z 5 is the same as z3, and x number 5x of nu is also this way. So this time the rotation that you need to align z4 to z5 is the same as the positive direction of rotation about x5, so this is going to be positive 90 degrees. And finally, going from 5 to 6, you have to look at the x's. X number 5 is this way, x number 6 is also parallel, so again that means you just need theta number 6. Now this time you have to move along the old z5 a distance of constant d6 to align the origins. There is no a is needed. And now you look at the z's. The z's, z5 and z6 are already aligned, so no twist is needed. So this is your DH table for your Stanford Arm, as you can see. And that is your robot. Now we can go ahead and use the A matrices and perform the forward kinematics, that for which I use MATLAB, okay? So if you remember from DH, each A matrix is basically made of 16 elements. The last row is always constant, 0, 0, 1. But the other rows, except for this element 1, 3, and 1, the other ones are functions of A's, D's, alphas, and thetas of each row. So we plug in the values for each one of the rows into this formula, right? So we set all the values of the first row here in this formula, and that gives us what? A1, then we plug in second row, A2, A3, A4, A5, A6, and finally T, right? The homogeneous transformation T, or you might call it H if you want. H of 6 with respect to 0 and the factor in base is going to be A1, A2, A3, A4 times A5 and 6. And this guy is going to be a 4 by 4 matrix which has the last row constant 0, 0, 1. Here you have a rotation matrix, 6 with respect to 0, and here you have position of end effector in base, 6 with respect to 0, right? Where this whole thing is 3 by 3, and this one is 3 by 1, and this one, as I said, is 4 by 4. So if you calculate all of this, and then, as I said, this minor 3 by 3 is the rotation matrix, that last column, except for the last element, is the position of end effector. And that is going to be the function of many of these variables. Some of the entries here in R or D is a function of maybe all variables. Some of them just some of the variables. But you can solve this basically symbolically. So if you want, you can just go ahead and say, well, I consider everything here as a parameter. Theta 1, theta 2, D3, theta 4, 5, 6, and then D1, D2, and D6. Right? And then get big formulas for the R and D of 6 and 0, which is what exactly I did here. So if you look here, I have this DH parameter matrix, which I used earlier in another video for the Puma robot. That's the same thing this time, except the difference that last time I passed numbers to it. This time I'm going to pass parameters, symbolic variables to it. And this is the Stanford forward kinematics. So you see I defined all of the joint variables and geometry constant as symbolic. This is the DH table directly coming from this DH that we have here. And I started my T as A1, and then from 2 to 6 I got all A2 to A6 multiplied, pre-multiplied. Use the simplification in symbolic toolbox, and then I said this part of it, as I said, is the position. This minor of it is the end effector rotation matrix. And if you look at them, they are not going to look super nice, okay? For example, if I just go ahead and copy the end effector position for you, just let's look at the Z component of it, which is like the simplest one, right? So this guy here is the Z component of end effector in base. So if I just copy that and write it somewhere for you, so this is what you get, right? So if I want to use abbreviations for sine S and for cosine C, then Z of the end effector in base, or Z of 6 in 0, it is going to be D1 plus D3S2 plus D6 times C5 times S2 plus D6 times cosine of theta 2 times sine of theta 4 times sine of theta 5. Okay, so that's like the simplest term. And then X and Y are longer, and then each component of that rotation matrix has a bunch of terms, right? So in general, as I said, they are going to be long terms, and that's obvious. Now here, to give you a numerical sense of it, we can just go ahead and plug in some numbers instead of symbolics, right? So we can just set up some numbers here. So here I used 30 degrees, 45 degrees, 60, 20, and 90 degrees for theta 1, 2, 4, 5, 6, and 20 centimeters for prismatic variable, and then I chose 25, 15, and 10 centimeters for D1, D2, and D6. And I do it again, this time numerically, and as you can see, now this is the position of the end effector X, Y, Z, and this is the rotation matrix, okay? So this is what you can do for analytic forward kinematics of this robot. You can change these angles and this distance D3 constantly and find the location and the orientation of the end effector, and you can even animate it or anything that you want. So hopefully the forward part of it, forward kinematics, is well understood. Now let's move to the inverse kinematics. the goal here is I give you the rotation matrix of end effector in base and the position of end effector in base, and as well as geometry of the robot. And then I say, okay, now could you give me the joint variables? So here I use the same R and D that these values have generated for me. So I expect the output of this algorithm, the inverse kinematics, will be these 6 values, right? So now I have that R, I have the D, I have the geometry. And so if you remember the method for the inverse kinematics of a 6DOF robot, which has a spherical wrist and can always have an analytic solution, is you first try to find the location of the wrist, which is here. So if I call this point W or P or whatever you want to call it, in our lecture I use point C, right? So if I call that point C, then the position of C in base is going to be what? It is going to be the position of end effector in base minus the vector that connects this C to the end effector. So if let me add a couple of more points. So if I call this origin of base, I call it point O, and call the origin of the 6th frame point E, right, for end effector, this guy here. Then I can say that the vector going from O to C is equal to the vector going from O to P, right, minus the vector that goes from what? C to E, correct? Because if I add CE to OC, that's going to be OP. So if I have these two vectors and subtract, that gives me the position of the wrist, point C. Now the question is, what is OP? Well, that's the position of end effector in base, so that is exactly this guy here, D of 6 in 0. So this one is perfectly given to me, right? What about this C in E? Well, I know this vector has a constant length of D6, and the direction of that is the same as direction of what? Z6, because if you see Z6, Z3 and 5, they're all in the same direction. So it is in the direction of fixed Z6, and the magnitude of it is D6. So if I want to write this, it is going to be that vector of D of 6 with respect to 0 minus the length D6, which is just a constant length, times unit vector Z6. Correct? And as I said, this D of 6 in 0 is given to me perfectly. If you want, you can call it R of 6 with respect to 0, doesn't matter. This D6 is also given to me. What about Z6? Is this also given to me? The answer is yes. Your rotation matrix R of C with respect to 0, if you know it has 3 columns. Each column of that is one of the unit vectors of frame 6 described about or aligned the axis of frame 0. So the first one is like x6 dot what? Dot x0, y0, and z0. The next column is all what? Y6. This y6 is dot producted with what? Again, with the same thing. x0, y0, and z0. And finally, we have z number 6, dot producted with what? With again x0, y0, and z0. So what is your z6, the unit vector of frame 6? Clearly that is what? That is the last column of that rotation matrix. That is what? That is z6. So that one is also given because the rotation matrix is given. Therefore, I can calculate what? The position of the wrist. So let's go ahead and do that as the first stage. So position of the wrist, I call it OC, this is equal to that D6 0 that we had minus D6, which is a constant distance, times the third column of the rotation matrix, these guys. So this is going to be R60 what? All rows and column 3. So this is the wrist position, right? Let me add comments for you as well. So this is the wrist position. This is the robot geometry and effector position with respect to base. And finally, end effector rotation matrix with respect to base. Okay, so now that I found the wrist position, I know that the wrist position is only a function of the first 3 variables, right? Because if you look, only rotation theta 1, rotation theta 2, and the prismatic value D3 are going to affect the location of wrist. Theta 4, this spin, is not going to change the position of the frame. It's going to change the orientation of frame 4, but not the position of the origin of it, C. And it's definitely not going to affect anything about 5 and 6. So this guy here, it is clearly a function of what? Theta 1, theta 2, and D3. And now the question is, using whatever number that I found, can I from here find theta 1, theta 2, and D3? Can I find these 3 joint variables just from the position of the wrist? If I neglect what? If I neglect the rest of the robot and just focus on the geometry of the first 3 joints, and give you the position of point C, which is the last point of the first 3 joints, can I find them? And the answer is sure, why not? So let me show you how you do that geometrically. So this is that robot without the spherical wrist. Let me add the base frame here. So the base frame was like this. This one was Z0, this one and this one you had. This one was X0 and this one was Y0. And the joint variables, if you remember, this angle was theta number 1. And then you had this angle here, which was theta number 2. Okay. Now, as we mentioned, the coordinate of C is only a function of theta 1, theta 2, and D3, as well as the 2 constants D1 and D2. What kind of function? Well, we can use pure geometry and do several projections here to find them, or we can go back to what we had earlier to forward kinematics and find them. So if we go back, clearly you see C is the origin of frame 3. And if it is origin of frame 3, then I can find the position of it with respect to 0, right? Through what? Through T of 3 in 0, which is matrix A1 times matrix A2 times matrix A3. These DH matrices. So what I need is really to use the first 3 rows, find matrices A1, A2, and A3, pre-multiply them to get this. Once I get this one, that is going to be a 4x4 matrix, and the last column of that is D of 3 with respect to 0, correct? And D of 3 with respect to 0, origin of 3 with respect to 0, this is exactly coordinate of point C. So if I want to find that symbolic or mathematical function, I can just use the first three joints and find those functions and then try to solve those functions for what? For the variables. So let's go ahead and go back to the code that we had, right? This code. And in this code, all I need is to define my variables symbolically again. So if you don't mind here, I use the same D1 and D2, but theta 1, theta 2, and D3, I will declare them all symbolic variables, right? I don't even need D6 in this case. DH table is the same table, and all I need now is I started as number 1 and then multiply 2 and 3 to it. So let's go ahead and do that. This one is now going to go to 3. And then all I need is to simplify T, and I only need the last column, which is all rows of 1 to 3 and column number 4. Okay, so this is all I need to get my functions, and I just call it test, or maybe I call it inverse position functions. And oh, it is asking for theta 4 now. That is interesting, because there is no theta 4. That's right. So how about this? There we go. So these are what we have. Or if you want, we can also introduce these guys, D1 and D2 symbolically too, and do it again, right? And now here, let me just copy these guys. So these are my functions, right? XC, YC, and ZC, for which I already found the number, right? These are my functions. So let me write them down for you here. This is equal to x of c, this is y of c, and this is z of c. Just remember that D1 and D2 are known. XC, YC, and ZC are known. Theta 1, 2, and D3 are not known. So the answer is, can I find any of them directly from any of these equations? The answer is no. Each equation involves more than one unknown. But it should not be impossible to solve here, because what I can do simply here is I can here, remember, I'm not doing the exact geometry thing. Can I found these through geometry as well? Yes, I can. You might say, well, show me that you can. And sure, anytime you challenge me, I'm in. So let me show you how to get these equations also through geometry, and then I'll show you how to solve it. But for example, D1 plus D3 sine theta 2, that's Z of C. How do I get that? Well, all you need is to look into this line of this member. So through origin 1 to origin 2, right? This guy here. If you look along this line, you might give these points some name if you don't mind. Instead of O1 and O2, I might just call them A and B. I can look in the direction of AB and call it AB view. If I look at AB view, I have the vertical axis to be Z0. And since AB is attached to this member, then the other axis is not really X0. It is going to be the same as X1 really. So it is going to be this X1 Z0 view. But all we care about right now is Z. If you look here, you have your D number 1 going up like this, and then you have the other member, which is D3 like this, and then you have this angle, which is theta 2. This is D3, this is D1, and clearly, if you project this point C onto the z-axis, you see this distance from here to here is d1 plus d3 cosine sine of theta 2. So this equation is very clear to see, right? So that one is very clear. I can easily see that. Now, for x and y of point C, you need to look at some other views or change this x1 to x0 so you can see it better. What you really can see is the distance that matters for x and y. One of them is d2 with theta 1, which is basically is like looking from the top. And this one as well, it's d3 times, again, theta 1. But this time you also have theta 2 involved. So the other view that you can clearly have is the top view. By the way, I have added for you these two projections and the summation of the two vertical projections, which give you z of c, and that matches the formula that we have. Now for the top view, if we look at this line connecting B to C, first of all, this line is perpendicular to AB in real life. Second of all, when you look in the top view, you're not going to see the entire length D3, right? If you go back to this AB view, you clearly see this is all that you'll see from the top. So what you will see from the top is clearly what? D3 times cosine of theta 2. This is all you would see. Okay, so if I want to draw the top view for you, you will see x0 and y0. You will see member with length d2 and angle theta 1. Now, where would you see it? Where theta 1 is 0, this member is aligned with y0. When theta 1 is non-zero, it further moves counterclockwise. So if you really want to plot this member at theta of 0, it is aligned with y0. When theta 1 is non-zero, it is going to go like this. The length of it is d2, the angle of it is theta 1. So this is point B, this is point A. And then BC is perpendicular to AB like this. The length of it that I can see from the top is d3 cosine theta 2. And clearly here, if I want to find the angle of this member, if I draw this vertical line, that angle is theta 1. So this angle is definitely 90 degrees minus theta 1. Okay, so now if I say, okay, what is x and y of this point C in the base? So what you need is, you need to find these two distances for x of it and add them together. So clearly your x is going to be this one, which is d2 times sine of theta 1 negative. So negative d2, let's zoom in here, it is negative d2 times sine of theta 1. And this distance here is d3 cosine 2 times sine of 90 degrees minus theta 1. And you know from tricks, sine of 90 minus the angle is cosine of the angle. So it is going to be d3 cosine 2 and then cosine of theta 1. And of course, that's also negative, right? So it's going to be negative this, negative that. That is equal to x of c. And I guess that's exactly this one here. Negative d2 sine theta 1, negative d3 cosine theta 1, cosine theta 2. Then if I say what is the y, then for y, you need to get this much positive. You have to subtract it from this much, which is negative, and that gives you y. This one is clearly d2 times cosine of theta 1, and this distance here is d3 cosine theta 2 times cosine of 90 degrees minus theta 1, which again, you know from trigs, this is equal, and that's downward. So it is going to be, this one is going to be sine of theta 1. Sine, sorry. So it is going to be positive d2 c1 minus d3 cosine 2 sine 1, and I guess that's exactly this term. Right? So now I have shown you where each one of these formulas are coming from. Geometrically, using our forward kinematics, you have seen each and every one of them, right? And now my question is, well, how can you solve for d3 theta 1 and theta 2? So one of the things you can do is this. I focus on the robot so you can see better. If now instead of lots of these projections, I just look at the distance between point A to point C, this diagonal here. What is this distance? Well, here I definitely ABC is a right triangle in the space. One side of it is fixed d2, the other side of it is variable d3. So this guy is clearly the square root of d2 squared plus what? d3 squared. Plus, I know where point C is. The question is, where is point A? And clearly, you see A is right on Z0 at the distance of D1. So point A is at 0, 0, and D1. So if I find the distance of C to this point A, that should be equal to that distance. And since everything is known in the distance between A and C, and D2 is known, the only unknown is going to be what? D3. So that's the first thing I do. I say, well, the distance between A to C squared is D2 squared plus D3 squared. And it is also equal to x of C minus x of A squared plus y of C minus y of A squared plus z of C minus z of A, which is d1 squared. The right hand side is perfectly known, d2 is perfectly known, so from here d3 is clearly going to be xc squared plus yc squared plus zc minus d1 squared minus d2 squared, the square root of that. Right? So that is your D number 3. Here we go. This is what I found, and I can call this guy, let's see here, I don't have any equation number, so I call it equation number 1. Okay, so now that we have D3, if we go back and look at that AB view, right, where ZC was D1 plus D3 times S2, clearly from here I can find S2. So S2 is going to be ZC minus D1 divided by D3. And if I call this whole ratio D, then theta 2 is going to be arctangent 2 of sine of theta 2, which is d, and cosine of theta 2, which is plus and minus square root of 1 minus d squared. Okay, so this one here is going to give me the equation for theta number 2. And finally, if I go back, and since now I have d and d3 and theta 2, that means I can easily go here and I can find the location of point B. Because I know point C exactly, now I know d3 and cosine 2, right? So I can draw basically a circle with center at C with radius of d3 cosine theta, and that gives me one circle. Then since I know point A, I can draw a circle with a radius of d2, that gives me another arc, and these two can intersect at basically two locations in general for theta number 1, right? And that's the same as if you look at these equations. Remember that now I have d3 and I have cosine of theta 2, this guy. So these are all taken care of, and d2 is also taken care of. So basically that's equivalent to solving these two set of equations, right? That's the same thing, and that should give you sine theta 1 and cosine theta 1. If I rearrange these equations in terms of sine theta 1 and cosine theta 1, you clearly see I will have negative d2, and then negative d3 cosine theta 2, negative d3 cosine theta 2, and positive d2. This is times sine 1 and cosine 1 is equal to x of c and y of c. And if I call this the right hand side and I call this the M matrix, then clearly sine and cosine of angle 1 are equal to M inverse times the right hand side. And that means your theta number 1 is going to be arctangent 2 of those two things, right? Sine 1 and cosine 1. So this whole set here will also be your equation number 3 that can give you your theta 1. So now let's go to MATLAB and code it up. So this is equation 1 for d3. This is that parameter d that we had for sine of theta 2. And then here I use the positive answer because in this case I know my theta 2 was positive, but in general, note that you have more than one solution for theta 2, right? And your M matrix, your right-hand side, the solution here involves a sine and cosine of 1, and then here I use arctangent to get theta 1, and if I run it for you here, look, your D is 0.2 and your theta 2 is 45 degrees and your theta 1 is 30 degrees, and that's exactly what you had over here, correct? So I could get my first 3 joint variables through the inverse position problem for the Stanford Arm. Now the question is, how do you find the last 3 joints? And for that we need to do the inverse orientation problem. And what we do here is, now we say, well, now that I found the first 3 joints, I can find the rotation matrix of frame 3 with respect to frame 0, correct? Because that's simply the rotation matrix coming from T of 3 with respect to 0, correct? If you remember, this is R30, D30, 3 zeros and a 1. And this guy was A1 times A2 times A3. We used it already for X, Y, and Z of point C. So now if you look at the rotation matrix part of it, this guy, We can easily get this because this is a function of theta 1, this is a function of theta 2, and this one has no effect really much on rotation except for maybe that pi over 2 that we had in negative pi over 2. Okay, so this is a function of d3 really. It's just there is a small rotation in it. But once I have this rotation matrix, which I can easily calculate, and we know, then I can find the rotation matrix of end effector with respect to frame 3. Because if I multiply that, pre-multiply it by R of 3 with respect to 0, the guy that I just calculate or told you how to calculate, that gives you R of 6 with respect to 0. And this one is given to me as a part of inverse. This one I can calculate. So from here, I can say R of 6 with respect to 3 is going to be a transpose of this R of 3 with respect to 0 multiplied by R of 6 with respect to 0. I can easily calculate this, okay? And guess what? This one, the orientation of frame 6 with respect to 3, if I go back and look at the robot, between 6 and 3, all that is happening are 3 rotations, theta 4, theta 5, and theta 6, only 3 rotations. And therefore, the orientation of frame 6 with respect to 3 is only a function of these last 3 joint variables. So it is another function like g of what? Theta 4, theta 5, and theta 6. Therefore, if I know that functions, I could, once I have this matrix, I could solve for theta 4, 5, and 6. And if you remember, for this inverse orientation problem, I told you that for the spherical wrist with the configuration that I showed you, we can easily say that is corresponding to the ZYZ sequence of the Euler angles, right? Because if we go back and look, you see your first rotation is happening about Z4, right? And then the next rotation is happening about Z5, or sorry, your first rotation is happening about Z3. The next one is happening about Z4. And if you look at Z4, Z4 correspond to what axis in frame 3? To what? To Y3. And then the next one is about Z5, and Z5 is corresponding again to Z of 3. So your order of rotation, Z3, Z4, Z5, about which the last 3 joint variables are happening, correct? Remember, this is where theta 4 is happening about, this is where theta 5 is happening about, and this is where theta 6 is happening about. Now, clearly your Z4, as I showed you, corresponds to what? To Y of 3, and Z5 corresponds to Z of 3. And this is, of course, Z of 3. So if you look at the sequence, it is what? Z, Y, Z. If we compare everything to only frame 3, the sequence is what? Z, Y, Z. So if I have the rotation matrix of Z, Y, Z for Euler angles, then this one definitely corresponds to that rotation matrix out of the Z, Y, Z sequence, which, if you remember, it was a rotation Z with angle phi, followed by a rotation y of angle theta, followed by a rotation of z and angle psi, right? The ZYZ sequence. Now here, instead of the order of phi, theta, psi, you have what? You have theta 4, theta 5, and theta 6. So theta 4 corresponds to phi, theta 5 corresponds to theta, and theta 6 corresponds to psi. Therefore, it is not really hard to imagine what kind of rotation matrix this one would look like. and then we say this rotation matrix is going to be equal to this R of 6 with respect to 3, which has 9 numbers in it, correct? And these 9 numbers of this rotation matrix, I can call them R11, 12, 13, and then all the way to R33, correct? So this is that rotation of 6 with respect to 3 that I can calculate. Here, it is going to be a function of phi, theta, and psi, and you know, based on the lecture we had on ZYZ sequence, this is going to be equal to. So I got this from our previous lecture, and if you remember from here, your angle phi, which in this case is your theta number 4, it comes from these two components, both of them multiplied by sine theta. So this is going to be arc tangent 2 of R23 and R13. These two guys. That gives you theta 4. Then your middle angle theta, which in this case is theta number 5, that comes from basically the square root of these two, which give you sine theta and then cosine theta. So this is going to be arc tangent 2 of plus and minus square root of these two guys squared. That gives you sine theta plus or minus, and then cosine theta, which is R33. And finally, your psi, which in this case is theta number 6, that is going to be arc tangent 2 of, that comes from these two guys, except here there is a negative sine theta, so you have to say R32 and negative R31. You multiply a negative, so both become sine theta times sine and cosine psi, and that gives you all of these guys. And so here, these are going to be my equations 4, 5, and 6 for the last 3 joint variables. So let's go ahead and do that. First, we calculate matrix R6 with respect to 3, and then from these formulas, we calculate the last 3 angles. So here I use the first 3 rows of the DH table. I found T of 3 with respect to 0. I found the 1 to 3, 1 to 3 minor of it, which is R of 3 with respect to 0 now. I transpose it, multiplied by 6, 0, found 6 with respect to 3. And then from the components of that, I found theta 4, 5, and 6. Here I used the positive square root because I knew my theta was positive. So I wanted you to get the same solution as I did. And if you look here, if you look at the numbers, you see that here we go. 20 centimeters, 45, 30, 60, 19, and it's almost 20, right? That's 20 degrees, that's 90 degrees, that's 60 degrees, and these are these angles. If you look at them, 90, 20, and 60. And then 30, 45, and 20 centimeters, I already found here. 30, 45, and 0.2. And those small differences are due to round of errors. But you clearly see that my analytic inverse kinematics does give me back the same solution that I could generate in forward kinematics. Okay? So here are the complete forward inverse analytic solution for the Stanford Arm, and if you paid attention, you see that we have so many different solutions, right? Because your theta 5 have 2 solutions, it has 2 solutions, and then if we go and look, your theta number, well, let's find it. Your theta number 2 also has 2 solutions. And your D3 here, we assumed it is the positive square root. Could it be negative square root? I mean, like this guy comes completely to the negative side, to this side. Well, it depends on the mechanical limits. Typically, the prismatic joints, most of the time, they move in a range that is not like completely symmetric, negative, positive, right? They typically work in a positive range most of the time, but if that's the case, then you have 8 solutions. But here, at least you see there are 2 solutions for theta 2, 2 solutions for theta 5, so a minimal of 4 solutions. Although again, I said you could go up to 8 solutions in general. So hopefully it was useful to you, and I will see you in my next video. Thank you.